Welcome, everyone, to today's CDAC webinar. I'm pleased to introduce today's speaker, Keith Phuthi from the University of Michigan and now UCSD. Keith completed his PhD in mechanical engineering at the University of Michigan. Keith uses atomistic simulations, mostly ab initio and machine learning methods to study energy storage materials. And his work is focused on metal hydrides, as you'll hear about today, as well as lithium-ion batteries, where he developed methods for determining material stability under different conditions of electrical potential, pressure, and temperature. Keith obtained his bachelor's degree in physics from MIT. He has a master's from Carnegie Mellon, and he is currently a postdoc at UCSD, where he's working on the development of sodium-ion battery materials. So welcome, Keith. We're looking forward to your talk.
Thank you. Thank you for the introduction. I'll go ahead and share my slides. Okay, I hope that's clear. Okay, so hello everyone. My name is Keith Phuthi. I'm excited to share my talk on the CDAC webinar. And today I'm going to be talking about the stability and structure of binary metal hydrides under pressure, under electrochemical potential, and under combined pressure electrochemistry. So some of you may have attended the talk by Karen Sugano a couple months ago. So she's our close collaborator, and this is work related to that, but this is gonna focus more on the computational aspects of that work. So I won't talk too much about the experimental side. I'll just highlight the connections, but this will be more computational talk. So I guess to give some motivation, why hydrides? So um, hydrides have been a hot topic for the past decade or decade and a half or so, mostly because of superconductivity, right? So there were a lot of predictions about how these hydrides could be superconductors. So materials with hydrogen ratios above 6, so somewhere around 9, 10 or more, could be high temperature superconductors. So in the figure on the left here, you see that these blue dots are experimental predictions for superconducting critical temperatures, and they span this whole space. But at the top, most of them are hydride materials. So this is why there's so much interest in them. And a couple of them have been experimentally verified to have these high superconducting critical temperatures. There's also the space of ternary hydrides, which is a bit less explored. It's a much bigger space, and it's an exciting pathway that people are taking towards trying to make room temperature superconductivity or close to room temperature superconductivity a reality. So this is one of the major reasons why hydrides are such an interesting material class now. But they've also always been interesting for other applications. One of the major ones is hydrogen storage. So hydrogen storage is an alternative to, say, batteries when it comes to energy storage for a number of reasons. It's very clean. Your only byproduct is water. Hydrogen has lots of chemical applications as part of synthesis pathways to make other chemicals. But one of the ways in which people have sort of considered hydrogen storage is through these metal hydrides. And the reason for that is that they have this very high uh, gravimetric and volumetric energy density relative to storing hydrogen in a canister, which has very much lower density and is also significantly less safer. So metal hydrides have always been sort of studied in this space. But what you can say about both the energy storage case and the superhydride case is that it seems that it's advantageous to put as much hydrogen in your material as possible. So while we're not going to be talking too much about sort of the properties or whether materials are superconducting or very good hydrogen storage candidates, what this work is going to be focusing on how we can put as much hydrogen as possible into a metal hydride, in this case, binary metal hydrides. Okay, so going into the details, so there's two ways at least that people think about loading hydrogen, so to speak, into a metal. Right, the first is the electrochemical pathway where you apply a potential U, and the reaction for that is given here. Um, Basically, you have your metal as a cathode. So here's a little schematic of that. You have a metal as a cathode. You have an electrolyte which has an excess or has is a source of these protons or hydrogen plus ions, and you have an external circuit applied which is a source of electrons. So when the hydrogen and the electron combine at the metal surface, a reduction reaction occurs, and then you form a metal hydride, and then the hydrogen can diffuse into the bulk, and you form your bulk metal hydride. So this is one pathway in which you can load hydrogen into a metal. The other pathway is pressure loading. So those who are familiar with diamond anvil cell experiments and the synthesis of high temperature superconductors will know about loading hydrogen using pressure. So you basically expose your metal to a hydrogen source. It doesn't have to be hydrogen, it could be some other material that is a good source of hydrogen. You pressurize that, maybe you do some laser heating to get things going, but essentially what that helps you load hydrogen into that metal. Now, the focus of our work is was thinking, okay, there's these two ways to load hydrogen into a metal. What if we combine both of these? And we call this the pressure potential or P squared approach, right? So if you have both these methods to load hydrogen into a metal, could you possibly load more hydrogen than you could with either method, right? Uh, and basically, what we're going to be talking about is showing that combined pressure potential increases the stability of higher hydrides. So you put more hydrogen in your material when you uh, use an approach that uses both combined pressure and electrochemical potential. So you take your whole cell and basically pressurize the system. Okay. So before I get into the details, I'll sort of introduce some of the basics behind the thermodynamics and kinetics of this process with a couple of examples. So, suppose you have a metal, you want to load some amount of hydrogen into that metal, right? For this reaction to proceed, right, the right-hand side must have a lower free energy than the left-hand side. That it has to be more stable than the combined metal hydride has to be more stable than metal plus hydrogen, right? So what that basically means is that the delta G for this reaction, the change in Gibbs free energy of the reaction, should be less than zero, right? So the goal of our theoretical work basically is to find these values for the individual G's. And once you have the individual G's, you can calculate a delta G and determine whether a reaction proceeds or not. So that's mostly what we're doing when we do sort of these theoretical studies. Now, in the pressure electrochemical case, which I haven't derived here, but it's you add just one more term, you have this accounting for the electrochemical potential U, right? This basically accounts for the change in the chemical potential of the electron, which is tied to the chemical potential of the proton. But your equation is only slightly modified, right? So we want to make sure this reaction, the delta G for this reaction, which now depends on pressure, temperature, and electrochemical potential, proceeds under a given set of conditions. Now, how do we get these G's, right? It depends on the approach used. So we do make some approximations. So for a solid species, for example, the metal hydride or the metal, we have to approximate G as the enthalpy at zero temperature. This is mostly to save computational cost, right? It turns out you need an order or multiple orders of magnitude more real dollars in computational cost to predict the free energy at finite temperature. So we don't do that. It also doesn't, the TS term, which would go from H to G, also doesn't contribute so much that it varies across different species. So it's mostly negligible. But that's not the case, of course, with hydrogen, right? Hydrogen is a gas at ambient conditions. If you increase pressure around 1 gigapascal to 10 gigapascal, it's a fluid and it's solid above 10 gigapascal. So we actually have to use either an ideal gas approximation in the lower pressures, but we need to use experimental fluid data in that intermediate region, and then we can only approximate it as a solid when it's solidified above 10 gigapascal. So I say we use G here, but really in principle, we approximate all the solids using the enthalpy, which is H of P at T equals zero. And this is the thing that we calculate using density functional theory. Now, a brief intro to density functional theory. This is a whole topic, but I just want to give an idea of what a density functional theory is. So it's basically a mapping from an atomic structure or some configuration of atoms to an energy, right? So if, for example, if I have the structure of YH2, right, I know where all the atoms are, I know where the hydrogen is, where the yttrium is, I know the shape of the unit cell. I put that in through a DFT calculation. Maybe I do a relaxation so that I minimize the forces and minimize the energy. Then I get a value out, which is the energy of this particular structure. And then I can do that for YH3, for YH9, or basically any other hydride material, right? So I do this for my entire database of materials. I get the enthalpy, which is simply the energy plus the pressure times volume, right? The pressure comes out as the derivative of energy with respect to changes in the unit cell, and the volume is given by the unit cell itself. So that's fairly simple to get the enthalpy from the energy. And then just to give more details on where this energy comes from, right? It comes from a variational minimization of something called the energy functional. And I write it out here. While I won't explain all the terms, what I want to highlight is this last term, which is called the exchange correlation functional, right? So this EXC is the major thing or major approximation in density functional theory. So in principle, there's an exact universal exchange correlation functional. We just don't know what it is. So many people have done a lot of work to approximate or to rather to fit this exchange correlation functional so that it reproduces experimental results. So if you're a DFT practitioner, what you would do is you'd have to make a choice of what exchange correlation functional is. So basically, you choose what approximation you make. So sometimes we find that some exchange correlation functionals are good for gases, some are good for inorganic solids, some are good for inorganic solids at extreme pressure, right? So there's always a choice that one has to make. And most of the error when it comes to DFT comes from this. Uh, and not to give DFT a bad rap, it still remains sort of the best balance when it comes to accuracy versus computational cost when you try to do these calculations. So I hope this gives a picture of what DFT is for those who may not be familiar with it. Now, given that, we know how to calculate energies, we know how to approximate Gibbs free energies. Uh, Now, how do we determine if a certain material or a certain combination of materials is stable at a given condition? So this is where the convex hull concept comes in. Right, so the convex hull is basically a way to determine what compositions, right, as a function of composition, what compositions are stable at a given condition. So, for example, if we look at this red line here, this is the convex hull when we have an applied potential of 0 volts, right? So in the extreme cases, so you have no hydrogen, you only have yttrium. So the most stable is yttrium, right? If you have no yttrium, you only have hydrogen, the most stable is hydrogen. Then if you mix 1 mole of yttrium with 1 mole of hydrogen atoms, what you'll get is that you will react that and you'll form YH2, right? And that's stable because it exists on the convex hull. However, if you were to take 1 mole of yttrium and 3 moles of hydrogen, you'd get this X here. But because it's not on this convex hull, it's not on this extrema, right? That means it's unstable. What you would have is rather than forming YH3, you'd form 1 mole of YH2 and 1 mole of H, right? So that's what this convex hull picture is saying. But this changes as you change the external conditions. So when you go to, for example, minus zero point 0.5 volts with your electrochemical potential, your YH3 is basically pushed down, or equivalently, the H end of this convex hull is pushed up because you're changing the chemical potential of the hydrogen electron pair. Right? What happens is that YH3 now appears on the convex hull, right? It becomes stable. So now you have both YH2 and YH3 stable. Everything else will decompose into either yttrium, YH2, YH3, or H, depending on how much of each uh, reactant you have, right? So this convex hull concept tells us something about which compositions are most stable at a given condition. The same applies for pressure, right? So if you look at 1 gigapascal, right, you have both this YH3 and YH2 being stable. And then if you increase the pressure, go up to 100 gigapascal, what this does, opposite to the electrochemical potential case, is that it pushes down this YH3 and pushes up YH2. So the YH2 stops being stable. And the only thing that you get that's stable here is YH3. And another thing that I want you to notice is that it can also lead to different phases. So at 1 gigapascal pressure, the Y3 alpha phase is stable, whereas at 100 gigapascal, the beta phase is stable. So both approaches, so more negative URHE and increasing pressure, they both increase the hydrogen content in your yttrium hydride, but the pressure has this additional effect where it also determines what crystal structure is most stable. And you need to know the crystal structure for you to be able to determine, for example, if it's a superconductor or if it has certain mechanical or thermal or other properties. So the structure also matters, not just the composition. Okay. Um, And just to give a sense of numbers and why this approach is interesting, so if you there's a calculation you can do with an ideal gas approximation where you can show that with merely zero point zero 0.03 volts of electrochemical potential, this has the same effect as applying 1 gigapascal of pressure. So that's from an experimental standpoint, right? It's much easier to apply zero point zero 0.03 volts than it is to apply gigapascal amounts of pressure. So there's a real advantage to the electrochemical case in terms of loading hydrogen, and we'll see how that affects when both are in play. Any questions, I guess, on the theoretical side before I move on? Okay. If not, I want to highlight that kinetics are an important aspect of this too. All I've shown so far are the thermodynamic aspects of this approach. So there's a lot of things happening in an electrochemical cell, right? You have hydrogen ions in solution. These hydrogen ions adsorb on your electrode surface. Maybe they diffuse across, maybe they meet other hydrogen atoms or adsorbed atoms, and then they can go off as hydrogen gas. This is called hydrogen evolution. Or your adsorbed atom could be absorbed into the bulk, and that's how you form the metal hydride, right? So all these processes are all happening at the same time, and many other side reactions as well. And with how quickly or the rate at which all these reactions occur is determined not by thermodynamics alone, but also by kinetics. So if there's significantly high transition barriers from going from one stage to another, then the rates of those reactions are going to be really slow. So kinetics plays a really important role in what you actually observe in an experiment. It's not just knowing what's most stable that's important. And I just wanted to highlight that as well. Okay, so there's two major reactions that we're interested in or that affect our results when we measure. The first is the hydrogen absorption reaction. So this is the reaction that we like. We like the hydrogen absorption reaction because it means our metal is taking up hydrogen. Then there's the hydrogen evolution reaction, which is a parasitic reaction, and we don't like the hydrogen evolution reaction, right? Because it basically depletes our hydrogen supply without forming any metal hydride. But in experiment, this manifests as hydrogen gas bubbling off, right? So these two are always happening at the same time. What we want is for the hydrogen absorption reaction to occur more frequently. So the delta G for HAR minus the delta G of HER must be negative for us to observe more hydrogen absorption than hydrogen evolution. And this basically boils down to a simple equation that's determined by the free energies of the components. Uh, so we have the free energy of the metal hydride. The lower the free energy of the metal hydride, the more we favor HAR, right? The higher the free energy of M, the more we favor HAR, and then the higher the free energy or the chemical potential of hydrogen, the more we favor HAR. So the way we think about how pressure electrochemistry works is that when you apply pressure, right, we favor HAR over HER because we are trying to minimize the total free energy G, right? So species with higher molar volumes, for example, hydrogen, are penalized more. So it affects the chemical potential or the G for hydrogen significantly more than it affects the metal, right? So when you compress or pressurize a solid, it doesn't change that much. But when you pressurize a gas, it has a huge difference on the properties and internal energy of that system. So hydrogen gas is hydrogen evolution is suppressed because the hydrogen gas molar volume is significantly affects the free energy of hydrogen gas. So that's how we think about why this approach is advantageous for forming more metal hydride than hydrogen gas. So let's go through some examples. I'm going to start showing some phase diagrams now, starting with yttrium hydride. So I'll block out some parts just to highlight things that I want to show right now. So let's take the example where it's only pressure. So the URHE is at 0 volts, right? If we go across as we increase pressure at ambient pressure, we have YH2, right? So basically that means you take an yttrium foil, you put it in the presence of hydrogen gas. It'll maybe perhaps slowly because of kinetics, but it will eventually absorb that hydrogen and form YH2. Right? That sort of happens on its own. It forms YH 0.2 first, and then it starts forming YH2. And then if you increase the pressure, above ambient pressure, you start forming this YH3 phase, right? This is the green part. Increase the pressure even more, you go through a phase transition. So basically, you go from one form of YH3 to the FM3M or the FCC type of YH3. You increase pressure even more, you start forming this YH4 and then YH6 and eventually YH9, right? And this is actually what's observed in diamond anvil cell experiments. Now, at the other end, if you just consider electrochemical potential, it's a bit more boring. But basically, at zero, at ambient conditions, again, you have this YH2. And then when you start applying this negative electrochemical potential, you start forming YH3, right? So it's much less interesting, but you also have this effect where you increase your hydrogen content as you apply this external condition. So the full diagram looks like this, right? So now we have this two-dimensional space where at any pressure and at any electrochemical potential, we have an idea of which is the highest hydride that can be formed. And that's the goal of this work. We were trying to make these p squared or pressure potential phase diagrams for different materials. Right, so there's a lot of information about what's most stable, which structure is most stable, and given that information, you can try and figure out how to synthesize different materials or pathways you can take, as well as what are the properties of that particular stable phase. So in case you're interested in the downstream properties as well. So for this yttrium case, pretty much all the hydrides you see here have been experimentally synthesized before, whether it's only through electrochemistry or only through pressure. So I'll highlight some details from experimental collaboration we have with Yet-Ming Cheng's group at MIT. Karen gave this talk a couple months ago where she showed this piston cylinder apparatus that she has that can go up to 1 gigapascal. And basically the if you go back to this figure, if we look here, 1 gigapascal is very deep in this YH3 region, so you're not going to form anything higher than YH3. But there was a clear advantage of applying pressure in the sense that when she applies pressure, her yield of YH3 over YH2, which we call the current efficiency, right? The current efficiency is basically you pass some amount of charge through your cell. How much of that charge is going to hydrogen absorption as opposed to being wasted on hydrogen evolution? So she found that when you increase the pressure more or about double the current efficiency is what you get compared over ambient conditions. So this means you're able to load hydrogen more efficiently using passing much less current, using much less energy, using this pressurized approach. And the main reason for this is because of how the thermodynamic driving force, or this delta G of the reaction I showed earlier, becomes more and more negative, right? So the more and more negative it gets, the more favorable it is for HAR to proceed over HER. So this was some nice experimental work from there that sort of gave us an idea of how advantageous this approach could be. Okay, so we can look at other phase diagrams. So we don't have experiments for any of the others, but we've done quite a bit of computational work. So scandium hydride is another one. The phase diagram is quite similar to yttrium. Uh, but for some of the phases you see here, for example, this ACH3, the HCP one, the P63MMC one, it's never been experimentally realized. The same goes for this ACH9. Uh, so this is a case where our predictions have something that's not really uh, as verified, but this could be a matter of someone going and doing the experiment and trying to look for these phases. There are other known scandium hydrides, for example, SH4, SH6, but I guess I don't show them here because they're at higher pressure, so hundreds of gigapascal. And then there's lanthanum. So lanthanum, of course, is a really important and sort of well-studied material, particularly in the superconducting space. This has quite a rich phase diagram. The LAH10 is a very high temperature superconductor, the same as YH9 actually, right? So this was synthesized in pressure cells on the order of hundreds of gigapascal. I forget the number, it might have been close to 200. And then you have LAH3, which is known, and that both phases of LAH3 are known, as well as LAH4. Now there's these not very these other phases, LH4, H9, LH2, H5. There have been reports of similar stoichiometries experimentally, but these are experiments from the 1930s and they haven't really been reproduced. But it's known that LAH2 readily forms in ambient conditions, and the same as YH2, but it does it more readily, right? If you expose lanthanum to hydrogen, it readily forms this FM3M or FCC type LAH2. So when we look at them together, we can start to see some trends. These are all group 4 metal hydrides. Basically the trends that you see is that as you go down the group, right, you more readily form higher hydrides, whether that's by applying an electrochemical potential or by applying a pressure. So lanthanum is the easiest to form hydrides, followed by yttrium, followed by scandium. Right, so there's a trend there. Which we can tie to things like electronegativity, right? Lanthanum is the least electronegative of them all. And we can study how the lanthanum or the metal ion, yttrium, scandium, lanthanum, transfers electrons or transfers charge to the hydrogen, right? So when you form a metal hydride, the hydrogen gains some amount of charge from the metal ion, right? And the amount of charge is somewhat determined by the electronegativity, right? If the metal is willing to give up some electrons to give to the hydrogen, then that's a good thing because you're going to form a more sort of homogeneous state for the hydrogen. So here, I guess what we're showing here is a couple of things. One is that when you go from a low pressure, for example, 16 gigabytes to gigapascal, sorry, to 96 gigapascal, right? The environment of hydrogen basically becomes more homogeneous, right? You're approaching this metallic hydrogen state, which is what you want in a superconducting state, right? So the pressure plays a big role in sort of making sure you approach this metallic hydrogen state, even though the electrochemical potential may stabilize a higher hydride, the metallic nature is determined mostly by pressure. So this is again, it's just to show that it's easier to form hydrides with lanthanum over yttrium over scandium. We looked at uh, a couple other hydrides as well. So here I'm showing vanadium hydride. So vanadium hydride has been uh, considered one of the better prospects for hydrogen storage. The reason for that is because it can absorb and desorb hydrogen fairly easily. Although this V2H phase, which we predict to be stable and is actually experimentally verified, is actually really stable, so it's very hard to get the hydrogen out of this V2H phase. But the VH2 phases that you see uh, readily sort of exchange hydrogen with the environment, and that's one of the critical criteria that you need to make a hydrogen storage material. It has to be able to both absorb hydrogen when you want to store it, as well as release hydrogen when you need to use it. So vanadium is interesting from that perspective. You don't form super hydrides, but you do have a pretty rich phase diagram of hydrides that can form. So uh, alloys or sort of ternary phases of this material have also been considered for hydrogen storage. Another material with a very colorful phase diagram is chromium. So chromium hydrides seem to be quite diverse. Uh, so you don't readily form chromium hydride at ambient conditions, right? The chrome doesn't react readily or spontaneously with hydrogen. But once you apply an electrical chemical potential, you form this CrH, this chromium hydride phase. And this is actually something that people study a lot because when you electroplate chromium, which is how people purify chromium, you always readily form this chromium hydride. So it's in some cases it's actually something you don't want to form, right? So this chromium hydride readily forms. There's also other chromium hydrides like Cr2H3, CrH2, and so forth and so on. But again, in the chromium case, you don't really have any superhydrides in this phase diagram. The hydrogen ratios are much lower. And this is generally a trend that you see across uh, periods in the periodic table. In fact, the later transition metals tend not to form hydrides very easily. So it's only the earlier transition metals and the group 4 metals are the ones that form the basically superhydrides most easily, as well as the rare earth, as well as the alkaline earth metals. So this is the phase diagram for CrH2. Some of these are not experimentally known, but Cr, CrH, and Cr2H3 are and CrH2 are all experimentally known. Okay, so those are the phase diagrams. But I guess I just want to give an outlook towards the future and thinking about this P squared approach. Now, of course, the obvious way to think about this is the ternary hydride. So there's a massive material design space there, right? Since it grows exponentially. So the number of materials you would have to consider is very large, and there's potentially tons of opportunities there to form hydrides for any kind of application, but as well as to see if there's an approach to doing pressure electrochemistry there. Uh, the electrochemistry in the ternary case, especially when you have two metals, becomes what I call fun. It's a problem that I would like to think about, maybe not today, but it's a quite an interesting problem because you have different redox potentials for different metals, and then that sort of affects what's going to react, what's going to form, and when certain reactions are going to occur. So it's a bit more complicated than the binary case, but certainly quite interesting. Um, but beyond hydrogen itself, the principle behind the P squared approach is that you're suppressing gas evolution because you're increasing the chemical potential of the gas species, right? So we could this principle need not apply only to hydrogen. It could apply to other electrochemical reactions where a gas is evolved, oxygen, chlorine, bromine, whatever gas may be formed in an electrochemical reaction. So I think there's interesting pathways there to think about how this approach could be used there. The computational approach would be slightly a bit more complicated. It turns out hydrogen is really nice because we use the hydrogen electrode as a reference, so it's quite easy to reference things and know what potential we're working at using what's known as the computational hydrogen electrode. With other species, it's not as simple. We'd have to come up with different approaches for that. But I think it's an interesting space to look at in terms of how the P squared approach can be used to selectively choose other reactions where there's gas evolution. And then to conclude, I think what we've shown and what our main takeaway is that this P squared, the pressure potential approach, is a pathway to synthesizing new or hydrides or to synthesizing existing hydrides at more moderate conditions. Basically, you form hydrides at lower pressure or you form uh, hydrides at low electrochemical potential. And one thing I think I forgot to highlight is to look at this phase diagram here is to highlight that this positive slope, this positive phase boundary, basically tells us that if we apply both electrochemical potential and pressure, we need more moderate conditions. For example, at ambient pressure, to form this superconducting Y9 phase, you need to go up to about 100 gigapascal. Whereas if you apply, say, minus 0.75 electrochemical potential, you can do it roughly at an order of magnitude less pressure, right? So the you going from 100 gigapascal to 10 gigapascal is quite a massive difference from an experimental standpoint. So the pressure potential approach, combined pressure potential, means you need more moderate conditions to make this work. Now, of course, experimentally, this is quite challenging, right? How do you make a pressure cell that operates at 10 gigapascal? That's sort of an engineering challenge that would have to be figured out. But the principle here is that when you combine pressure and electrochemical potential, you need you need more moderate conditions, or you don't need as extreme conditions to form the same composition hydride. And the other takeaway is that when you pressurize, you increase the current efficiency or the rate efficiency of forming a particular hydride, right? You're more efficient in how you synthesize your hydride as opposed to just only applying pressure or only applying electrochemical potential. And with that, I'd like to thank my group. So I completed my PhD last year in the Viswanathan group at UMich, which was at CMU before. And I thank Dr. Pinangon, who's actually one of the people who sort of founded this idea, as well as our external collaborators who did the experiments at MIT and the funding sources. With that, I'll be happy to take any questions.
Thank you very much, Keith, for a great talk. It was very clear. Questions, comments from the audience. Just unmute yourself, put your comment or question in chat, raise your hand.
I had a question. Hi.
Hi.
Hi. Very nice talk. Thank you. I had a question about the current efficiency. So, I understand, we are theoretician, but I was wondering, like, uh, theo- what, like, can we, like, quantify the current efficiency uh, uh, of the, like, in experiment in compared to, like, the theoretically calculated parameters, like, how can we quantify and, like, experimentally how we can increase the current efficiency?
Yeah, so the current efficiency in this case is an issue of kinetics. Uh, so YH3 is stable under the conditions that we explore here, right? So it should form YH3, but how long it takes to get there is determined by the kinetics. So in this case, there's a kinetic aspect of it where sure, the YH3 is becoming more stable because it has this lower delta G, but this delta G is also related to the kinetics in that it gives you what the thermodynamic driving force is. So how much do you really want to form YH3 over YH2? And that is correlated through things like what if you're familiar with the Bell-Evans-Polanyi relationship, that's related to the kinetics. So I wouldn't say I'd be able to computationally quantify the current efficiency, right? It's a mixture of kinetics and thermodynamics that goes into that. So I wouldn't say I can quantify it computationally. It's just something you'd have to measure. But the trend is sort of the more favorable the reaction, right? The lower the delta G, the more likely or the better your current efficiency is going to be.
Actually, thank you. Yeah, that answers my question. Basically, I was curious about, like, the right hand axis of the delta G, and so yeah, it makes sense that the kinetics from the
Maybe
kinetics
to
is good.
follow up, yeah, I see Karen is on. I don't, did you actually try to quantify the kinetics versus the thermodynamics or the thermodynamic baseline, Karen, in your experiments?
No, we didn't. We did not. Yeah, that would kind of involve like what's like the hydrogen absorption energy, kind of figuring out what the hydrogen evolution kinetics is on YH2 at different pressures, and that would have been a very involved process. So we didn't get around to doing that.
Yeah, that's what I thought.
Yeah,
Okay.
it is. So some of those things are also possible computationally, but it is also a lot of work to sort of track out each reaction, figure out the kinetic barriers of each reaction, and come up with the reaction network. And it's a lot of work. Yeah.
Right. Christoph, you have your hand raised?
Yes, thank you very much for this very interesting lecture. I wonder what is going on with hydrogen inside the bulk metal and how these interactions change when you increase pressure or when you use electrochemistry and possibly both electrochemistry and pressure.
Yeah, so the hydrogen essentially has to diffuse into the bulk, right? So that's again another kinetic process, right? There's a barrier to how much hydrogen is absorbed. So it has to diffuse slowly into the bulk, and that the bulk has to change from the surface going in. Now, the crystal structure, right, changes depending on how much hydrogen is absorbed, and it also changes due to the pressure, right? Again, depending on the pressure, right, you can either form, for example, in YH3 case, you can either form an FCC phase or an HCP phase. So the pressure affects the crystal structure as well as how much hydrogen is absorbed affects the crystal structure. And there's some amount that has to diffuse through the bulk for you to happen. So the middle of your foil is the last to form basically the 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 metal hydride. So you have to run this process long enough for that to occur. So it might be a slow process depending on the kinetics. It might be a fast process, but there's a kinetic aspect of it there as well. I'm not sure if that answers the question.
But it has to interact. I mean, hydrogen is carries some electron density and
Yeah.
it goes inside the crystal lattice, which is in the case of say lanthanide or other atoms. They have very big amount of valence electron density. So this diffusion is, I mean, is associated with interactions. So
Yes.
what kind of interactions do we have there? Does it form any compounds, any chemical connection to say these ions which are present in the crystal lattice? And by the way, you consider only the average crystal lattices, whereas real lattices, local lattices, they can be quite different because that could be seen from such studies as say per distribution function or reverse Monte Carlo modeling. So the average structure maybe isn't the best structure to be considered because the variation of in the real structure is big when we think about positions of ions in the crystal lattice.
Yes. Yes. So here we only consider bulk non-defected structures, right? We assume the hydride that's formed is non-defective, it's pure, right? And yes, in the real case, there's vacancies, there's interstices, there's the hydrogen is going into different sites in the lattice, and that changes the local strain, that changes the local distribution of the electronic density of states. There's a lot going on. Definitely, I see that point. But I guess for simplicity here, we're interested in the thermodynamics of that convex hull in terms of which hydride is formed. Now, in reality, when I say there's YH3, what it is actually YH3 minus delta, right? There's a delta there of there's vacancies. You haven't filled up all the YH3 sites. Maybe not all of them will be filled up. It's YH2, but maybe it's YH 1.98, right? So there's a ton of things in reality that happen in the experiment, but here we just consider, as you said, the average of what the final structure will be and what the final structure that's on the convex hull is at a local level. The interactions, we don't delve deeply into it that much in terms of figuring out what that is. And I think an approach that Russ is super interested in as well, figuring out when you have non-stoichiometric hydrides, how does that affect the electronic states? How does that
Yeah.
affect the different electronic properties of the material? And I think that's certainly an interesting approach. We were doing this high throughput, so we did this for all these metals all at once, all these tons of DFT calculations. So we needed to find something interesting first, and then you can deep dive into how that can be affected on an individual scale.
I'm also sure that if you combine this with neutron diffraction studies or quantum crystallographic studies, you can get really very interesting information. Thank you very
Yeah,
much.
thank you.
Yeah, just to follow up, the trihydrides are notably substoichiometric, and that's been known at low pressure for many, many years. And there's a huge change in electronic properties as a function of hydrogen between, YH2 and YH3, for example. And you can tune that and actually measure at low pressure that stoichiometry using various techniques. It's harder at higher pressure, but at low pressure, it works pretty well. So good point. Skylar, do you have a question?
Yeah, so very clear talk and everything is very interesting. So I have a very simple question because you can calculate the free energy of all these hydride. Which hydride you think of this at electrochemistry and high pressure can be stable at relatively low pressure, especially ultra high vacuum?
So in this for the ones I showed here, that would be lanthanum hydride. So lanthanum hydride is the one that most readily forms hydrides. We have done other studies, but because we didn't have enough sort of crystal structure data, I think things like rubidium hydride, so going down period one of the, sorry, group one of the periodic table
Mm-hmm,
is
mm-hmm.
also interesting. The alkaline hydrides are interesting in that regard. They're much more rigid. They're not sort of as diverse as transition metal hydrides, but I think rubidium hydride is one that forms high hydrides quite easily as well because it's so reactive and willing to give those electrons away to the hydrogen.
Okay, so most of the interesting hydride with a lot of hydrogen inside of that is not very stable at low pressure.
Yeah, no, superhydrides. So things with that superhydrides where H where with hydrogen ratio more than 6, we don't find any at ambient pressure.
Okay, thank you.
I think there's a question in the chat. So the question is, after forming a hydride that is only stable at an applied electrochemical potential and certain hydrogen pressure, what happens when you stop applying potential? Thermodynamically, the hydride would decompose. But taking CRH, for example, does it remain stable after removing the applied chemical potential at ambient pressure? Is CRH metastable? So the metastability is determined by the kinetics, right? If there's a kinetic barrier, so in principle, when you remove the electrochemical potential or remove the pressure, it will decompose back down to whatever is most stable, right? But whether that happens or not is determined by the kinetics. So if there's a big barrier to that decomposition, it might stay as the hydride for quite a while. And this is part of the consideration when you look at hydrogen storage of you form this hydride, how easily do you release that hydrogen? So in Karen's case, the wife she did to quantify the amounts, she did Rietveld refinement, but she couldn't do it in situ. So she would actually have to take out the hydrided foil and measure X-ray diffraction pattern and quantify it that way. So the YH3 was, even though it's not stable at ambient conditions, right, it survived long enough for her to actually characterize it. So there's some kinetic aspect again to whether or not it decomposes, but it eventually does decompose.
Right. Yeah. So I mean, there are certain hydrides like for hydrogen storage that are metastable that are very useful that I'm thinking about. And yeah, I mean but that's the big question. Yeah, like so for it to be useful, I guess you would for hydrogen storage you would probably want something that would be stable at ambient. But yeah, but thermodynamically, I guess so. Like yeah, this chromium hydride case, I guess experimentally it does remain there, just I guess kinetically stabilized by maybe chromium oxide or something. I guess with electroplating or something. Just hypothetically, like what keeps it stable? Because like looking at this phase diagram, thermodynamically, it should just decompose back to
Yeah.
chromium, right?
Yeah,
Yeah,
if there's
after removing the
if
potential.
there's something like an oxide layer blocking hydrogen from leaving, or there's the surface is different from the bulk, or there's diffusion through the bulk is a bit more slow, perhaps
Yeah.
because of the electronic structure, then many things come into play there. Yeah, definitely.
Okay, thank you.
There was an earlier question in the chat. Ron asked about yttrium, why you studied yttrium. Actually, it's a good question because the higher hydrides of yttrium are harder to make than for lanthanum.
Yeah. Yeah. So why yttrium? So yeah, so this was early on in the work. So we'd done the first phase diagram. So this was work done by Pinran Guan. His phase diagram had YH9 being formed electrochemically only. So we were like, okay, YH9 superconductor. We don't have a lot of precedent for people doing electrochemistry with lanthanum, but there's tons of people doing precedent with yttrium because turns out YH2 to YH3 transition is transition where you go from insulator to a semi-metal, so the material becomes transparent. So there's been a ton of work by like Philips and other companies trying to make switchable mirrors. So there's a ton of precedent for yttrium. Uh, we thought we could form YH9 electrochemically and at low pressure. So that's why we studied yttrium as the first step. And sort of the experiment, setting up the experiment took a long time, as I'm sure Karen will let you know. So that's why we studied yttrium first as opposed to lanthanum.
Yeah, thanks. Sadler, do you have a question?
Yeah. So you alluded to that combining metals is going to be exponentially harder because of the increase in phase space. But in terms of this hydrogen absorption versus hydrogen evolution, people who want HER, that's the main way they do it is they alloy platinum or they make intermetallics, of platinum with some other metal. And so could you learn from that in terms of what alloys are good for HER and therefore those would be bad for this, trying to do HAR?
Yeah, there's certainly a lot we can lean on from that hydrogen literature in terms of the effect of different alloys on hydrogen. The ultimate goal, of course, is you want to form some hydride with some property, so like the downstream property matters. But yes, I agree. Because the hydrogen community wants the opposite, right? They want way more HER than HAR because they want to produce hydrogen gas that they can store. So if we go for the opposite approach, maybe that's an interesting space as well. Yeah, it's a great comment.
So coming back to the superconductor application, one thing you didn't comment on is the role of dynamical stability of these phases. And you can calculate that, of course, at the quasi-harmonic or the harmonic approximation. And we know experimentally that you can stabilize these phases that are superconducting well below the pressures at which they are dynamically unstable because of various anharmonic effects that stabilize those phases. So maybe a comment on that. And then secondly, even if you are able to stabilize these phases at lower pressure and therefore different volumes relative to the case without an applied potential, the TC will be different because the TC is a strong function of volume.
Yeah.
So can you comment on both of those?
Yeah. So in the first case, sort of the dynamic stability comment, yes, I would have loved to have done quasi-harmonic approximation on all of these. It would have completely destroyed our budget, unfortunately. Uh, so that's something that's sort of a next level to consider after you do the screening and you say, oh, maybe lanthanum is interesting. Let's go and look at this lanthanum hydride in more detail. So that's definitely something worth considering in future studies when you narrow down your scope and choose a certain set of metals, especially if you go to the ternary case, that's something you might well want to do. Um, Maybe machine learning potentials and machine learning methods will help us do that much faster. That's something that I've always been interested in myself and have worked on. So that might be a pathway to doing that in the future where we account for dynamic instability and sort of vibrational effects to the free energy. And then on the second comment, the pressure, or I guess the volume, has a strong effect on the superconducting critical temperature, right? So this is my comment on how the pressure really determines how metallic your hydrogen is. It determines how has a big effect on the electronic properties of your material. So you still need to know what crystal structure it is. You still need to know the unit cell volume and all those things to be able to know whether you're going to form a material with the right properties downstream. So in this electrochemical setting, right, this is uh, a very huge uh, engineering problem of how would you do electrochemistry at say 10 gigapascal. You have an electrolyte, you have an anode, you have a counter electrode, you have all these complicated things. You have to keep all your resistance measurement contacts soldered on. It's uh, challenging, is what I
I
would say.
agree. Absolutely.
Yeah.
But these calculations are very important to guide that
Yeah.
and to actually suggest particular systems that should be targets for these very hard experiments. Another question from Christoph?
Yes, we usually characterize superconductivity by absence of electrical resistance or the Meissner
Yeah.
effect. But what is a theoretical characteristic of superconductivity? If you apply some theoretical frames, quantum mechanical ones, so what kind of theoretical parameters would characterize superconductive state?
Yeah. So that comes mostly from the electronic structure as well as from the crystal structure. So there's so the most commonly used approximation to estimate a superconducting critical temperature in these calculations that have been done is something called the Macmillan-Allenstein formula. And that's it's a bit of an empirical fit. And the parameters that pop out of that expression are that you need what's known as a strong electron phonon coupling, right? So this has to do with the vibrational states as well as the electronic band structure. So you need that coupling to be very strong on the order of more than one. You need a very high density of states near the Fermi level. So this has to do with the electronic structure. So you have to be metallic. And at the Fermi level, you need a relatively high electronic density of states. So those are the two major ones. They don't interplay perfectly, but in general, strong electron phonon coupling, high density of states. So the more metallic that hydrogen framework is, the better the likely better the superconductivity. It's not always the case. Sometimes you have parameters like that and the superconductivity is much lower, sometimes it's much higher, but that's a general rule of thumb. Yeah.
With even advanced theoretical methods, is the state of science at present such that you can predict critical temperature, and these predictions are confirmed by experimental outcome?
Yes. So we are actually in a state where we get ballpark pretty much errors are typically like something like 30%. So for example, I think Russ might correct me here. Lanthanum or yttrium was predicted computationally first to say this has a superconducting critical temperature above 200, and then experiment went and found that. So we are at a point where we can do it computationally and get pretty good estimates of what the critical temperature is. So theoretically, yes, we can do that. Once we know the structure and we dig deep into sort of its properties, we can do that.
So there is only last step to be done to find somehow relations which would allow us to predict this high temperature, ambient pressure, superconductivity.
Yeah. Yeah. So yeah, we can that's certainly that's something a lot of people are working on in terms of trying to find which materials or design rules for these superconductors to see which combinations of materials what lead to high temperature superconductivity. I think sort of the lanthanum I think is sort of the one where in the binary space, which is pretty well explored, is where people found that, and I think ternary is where people are looking now. There's a lot of work going on for ternary hydrides to try and synthesize superconductors.
Thank you very much.
Yeah,
Okay.
that's right. And the good news is those systems look like conventional superconductors. So
Mhm.
BCS at various levels of approximation work quite well.
Mhm.
Right. Okay, thank you very much. If there are no more questions, great discussion, great talk. Thank you very much.
Right. Thank you for having me.
Okay, we'll see you next time.